Okay. All right, so luckily for us, what kind of graph is this one? It's linear. So y-intercept of positive 2 and a slope of negative 3. Okay, so we've got our cute little line here. All right. And so what it wants you to do is define the slope of the curve of f at x equals, and that's your number that I gave you. Okay, so we're all going to do a little different problem here. Mine is negative 3. We're going to use the limit definition to do that. It's a little practice with that, all right, from what we talked about yesterday. Remember, when we're doing that limit definition, limit as h approaches 0, f of x plus h minus f of x all over h, okay? And so then we're going to plug in our x value for x and then compute from there. So mine would be f of negative 3 plus h. Just to give you a little more practice on this, we're going to do it a couple of times. Use my x value, you're going to use your x value. And then we just replace it in that difference quotient where there's an x. And then plug it into that function up there, simplify. What did we say should happen every time yesterday when we do this definition? The constant should cancel out, okay? If not, we did some arithmetic wrong somewhere along the way. Okay, the constant should cancel out. And so now this is the class participation part. We get to use stickers in the big graph paper. I'm excited. Okay, so what you're going to do is we're going to go over here to the board behind Madeline and Parker. And there's a graph for question 3, which is this one. There's one for question 5 and one for question 6 over there, okay? And we're going to plot the slope that we have for our x value. So at negative 3, I'm going to put a dot when y, or my slope, is negative 3. Okay, so that's what I'm going to put. So as you finish your calculation, you can come over here. And all I got are little smiley stickers. So we'll use those. So I'm negative 3. There's one over here.
I got the same thing. Go around, my thing. So crazy.
We're learning good stuff today, learning good stuff.
really, really took the preparation.
I think they're all the same.
Yeah.
I just want to do it.
Yeah, I did mine.
Let's say.
I don't know. I'll get the one that looks
Just grab one. It
Not-
takes too long.
I literally no.
Orange, green literally looks the same.
Green or pink? Yeah, I'm gonna go green because they're green is the one
So,
I gotta go on the line.
OMG is literally zero. OMG is literally zero.
First try.
Oh, I was hoping that was the entire year. Oh, there are no secrets, sorry.
All right, so let's do this. Let's copy that graph. All right, next to, okay. So this is our derivative graph. Another way to talk about it is it's our slopes graph. Okay, and what do you notice about all of our slopes? They're all the same, okay? All right, so we get this horizontal line. Does that make sense that if I have a linear function, the slopes would all be the same?
Yes.
Sure, okay, it makes sense. So what do we think would be the slope of the curve of f at x equals 53? It's still -3, okay? So it's still -3. Right? Okay. Cool beans. All right, so we're just I love things where we look at patterns and things like that. All right, so in questions 5 and 6, we're going to do the exact same process again. Okay? In 5, we're going to look at g of x. G of x is equal to x squared. And then in 6, h of x is equal to x cubed. And the algebra is going to get a little bit nastier there with that x cubed. Okay? So you might need extra space, all right, to do that one. But we're going to do the exact same thing. Okay? We're going to use our x value. We're going to calculate those limits, which we said was the derivative, right? So we're going to calculate those limits and graph them, all right, and see what we get, okay? So let's start with g of x. If I graph it, what does that function look like when we graph it? It's a parabola, all right? So what, 2, 4, -2, 4, 3, 9, 4, 16. Okay, so we're having to approximate based on how they labeled this graph. Okay, so we know that's g of x, right? And then now let's do that limit definition again. All right, using your point, let's do our limit definition. Do you think we're going to all get the same answer this time? No. Okay, we're definitely not, just because it's not linear. All right. What?
My dot just below that.
Oh, sorry.
Just put it there and then write an arrow below. Yes, it would be 2H, 2 plus H. Don't make me. Don't.
It's kindness week.
I don't want to be kind. Stop it.
Don't mind me.
Maybe this big wrapper would come in so handy.
Sorry.
Stop touching me.
I can't.
Wait a
My dot
minute.
is below the graph.
Hold the phone. Oh,
It
wait.
is.
Oh,
Sorry.
wait,
Mary.
it's gonna be off the graph. No.
You remember? No,
Gosh.
Do what?
No, we go around the graph.
Yeah, I just haven't gotten that far yet.
Oh,
No, for H.
Well, no, that's
Yeah.
where I was first, and I don't have to always be
Cubic, I know,
first.
but
Yeah, for the cubic, no, but for.
For the quadratic?
Yeah,
Yeah.
yes. I was
I haven't done the cubic.
Yeah.
Wait, I need to check. What is the, okay.
Oh, Lord have mercy. Yeah.
Sorry, it fell off.
I didn't expect stickers to cause this much issue.
Yeah, my F is 0, which is 0.
I'll remember which side. I think it's this side. I thought it's
Okay, so let's take a look at this one, all right? So take a look over there at our slopes graph. What do you notice about the one from the quadratic? What is the slopes graph? It's linear. So I started with a quadratic function and my slopes, my derivatives, formed a linear function. When we started with a linear function, my derivative, my slopes formed a constant function, okay? So, that being said, let's go back and let's copy this. What do you notice about that linear function that we created? What's its x and y intercept? 0, okay? What's its slope over there? 2. So we went up 2 and over 1, up 2 and over 1, same way down 2 and back 1. Okay? What would the equation of that linear function be? 2x. Okay? So we found our derivative to be 2x. Okay? Here we have y equals x squared. We found our derivative to be 2x. Okay? So now let's answer the next question, right? Because every x value I use should follow the same pattern, okay? And so if we look at part C, what do you think will be the slope of the curve at x equals 3? How are we going to find, at x equals 53? All right, how'd you get 106? It's 2x, right? So we take 2 times 53, and we'd get 106. That is correct. All right. So basically, we found g prime of x was 2x, and we evaluated that derivative at 53 and got 106. Okay. So that function, that 2x function, the derivative function, helps me to be able to evaluate the derivative at any value, x value we might need. Okay? Let's do it one more time. All right, now, what's your guess of what the slopes graph, the derivative graph, is going to look like for x cubed? I think that's a good assumption. All right, so let's do that. Using the limit definition, this time's going to be a little bit tougher, but if I go ahead and graph x cubed so that I've got it, 0, 0, 2, 8. Do your limit definition because we're going to have to do that. Solomon, your point's -3. I've been doing it for you all day. They say, hey. Just Laura. Laura says, hey.
Sam says that he hates you so much.
Oh, that is not nice.
I did say that.
Oh, hey, that's not
How does that make you
Kind
feel?
this week. How does that make you feel, Solomon?
That's you, bro. All right, I'm going to do some algebra right here, y'all.
Yours is me. I just said yours is me. Wow, you so much.
I'm not one of them.
I'm so glad.
I accidentally did it.
I'm out of room. Oh, that would be a positive.
Number 1.
27h minus 9h squared plus h cubed.
Mine's -6.
I was like, is it not going to fit? I don't think mine's going to fit.
Yeah, mine's
Yeah, I don't think mine's going to fit. No. Okay. So I think if you're past -2, it's not going to fit. Yep. Is that what we're seeing? They'll fit on the piece of paper we've got over there. Okay. What should happen at +3, though? If my -3 is 27, what should also happen at +3? It should be 27 if it's quadratic. We're assuming it's quadratic. Okay? So if you have the negative version of somebody's positive version or vice versa, y'all can double check each other and make sure you're correct. Okay? So if you've got -6, find out who's got +6 and check each other.
Anyone got -0?
Who has positive?
You're a lone man. You're an island, Sam.
Wrong.
What if it's not zero?
Wait, so who had 2?
How about
Neve, like, what did you get? Like, isn't that so crazy?
It's so crazy.
Crazy.
I should actually just write out crazy.
No, don't start this.
Well,
I'm gonna die.
Oh my God. That is serious.
I'll hold eight.
I just
Hold eight.
approved
I'll hold
that.
eight.
That's not kind of.
Definitely not kindness. Sorry, but.
Congratulations.
Good job. Everyone gets a stick.
Bro.
There are 2 periods that don't have a
0.
Oh, the.
The 4x4 gets an orientation that's involved.
mine doesn't really do
Okay, does everybody see what I did here when I cubed it? So I squared it, because I already knew that when I done it before, and then I multiplied it by the last -3 plus h, okay? Because I'm not good at doing perfect cube all the way out, so that's how I have to do it.
Yeah, I did the same.
Okay, so I take like, because that's like 3 parentheses multiplied together, I take 2 of them, because I can do that one quickly, and then multiply by that extra parentheses. Gives me lots of terms, right? But still, did you notice the mistake I made right here? If I cube a negative, what do I get? A negative. So this should be right here a plus 27 right there, because it's minus a negative. Okay, it's going to be those little things. Grown, 50 years old, still did it. Okay, like it happens. Okay, so you just got to be careful. Bro. Fire. Okay, so let's take a look at this. Somebody that's over there close, Parker, that'd be you, I guess. Give me the ordered pairs. It is quadratic when we look at it, but let's get the ordered pairs so we can kind of maybe try to figure out a function.
0, 0.
Okay, that's a good one.
1, 3.
Okay,
-1, 3.
okay,
-2, 12. And 2, 12.
okay, so it's going, oops, sorry.
Count that correctly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 12.
It is 12. Okay. So it is a quadratic. It's not shifted off the origin. Okay. What do you think is the equation of that quadratic? 3x squared. Yeah, I would agree. H prime of x that's a 3x squared. I mainly get that from going over 1 and up 3. So it's got that stretch, that vertical stretch on it. So 3x squared. So that being the case, what's going to be the slope of my curve at x equals 53?
Very, very high.
It's going to be big, right? H prime at 53 would be 3 times 53 squared, which is going to be a big honking number. There you go, 8,427. So that's a pretty steep slope. Okay, that's a pretty steep slope. Now, why do you think we took all the time to do this, right? To look at a function, take some points on it and look at its slopes, then look at the slopes graph, the derivative graph. Why do you think that's important, or what do you think it shows me? It's leading me to the shortcut that's coming, yes. Okay, it's leading me to the shortcut that's coming next week, maybe Friday. Do what? Yeah, we can kind of look at the patterns of what's happening with the slopes, right? It's telling me, well, you know, if I start with something linear, my derivatives should be constant. If I start with something quadratic, my derivatives should follow a linear pattern. So it's all pattern based, okay? And the nice thing about that graph is it helps me see all the slopes at once. Okay? And then not only does it help me see all the slopes at once, it helps me to find a general equation or find a general, let's say general equation. General equation for the derivative so we can evaluate the derivative at any point, or so we can find the slope at any x value. All right? Because let's be honest, that limit process, if I had something that was to the 5th power, or if I had something that was trig, like that's going to be a pain, right, to do that whole limit process. So if we can come up with a pattern, all right, then it's going to help me, because here's the important piece as well. The derivative is also a function, okay? So when I started linear, I got a constant. When I started quadratic, I got a linear function. When I started cubic, I got a quadratic function. So the derivative is also a function. All right, it's a function of x, and it's super useful in that regard. Okay, now what I want to do next is just to kind of look through some more. We're stuck in this limit process for just another day or so, okay? And then we're going to get out of that limit process, and you're going to love derivatives, okay? But until then, we got to stick with it for just a second. But it also opens up some opportunities for me to do a lot more problems, okay? And so I want to kind of show you what it's going to look like, all right? So let's go right here, all right? So this one says to find the derivative of f of x equals x squared minus 4x. Notice, did it give me an x value to plug in? No, so we're going to keep it general. We want to find the general derivative function, and we can do that with the limit process, okay? So here's what we'll do. When we're, when we're doing the derivative, we're going to actually take that big nasty definition, the limit, as h approaches 0, f of x plus h minus f of x all over h. Now, this is where people look at me and go, oh, I miss math with numbers, okay? Because we're going to do some things moving forward where sometimes there's just not any numbers involved, all right? It's all variables, okay? But we're going to use the exact same process we just did. So the limit as h approaches 0, okay? So x plus h squared minus 4 times x plus h, all right? Minus, and this I'm going to throw into parentheses, x squared minus 4x, okay? Because I just plug in x into the function. I want f of x. And then we're going to divide it by h, okay? Lots of algebra to do right here. Limit as h approaches 0. Woo! X squared to xh, h squared minus 4x minus 4h minus x squared plus 4x. Woo! All divided by h. Now, because we don't have a number to plug in, we don't have a constant term, but what do you notice happens? Above the stuff goes away. Everything that doesn't have an h should go away. Okay, so if it doesn't contain an h, it should go away. Let's double check and make sure that happens. X squared and a minus x squared, negative 4x and a positive 4x. So it does indeed happen. Okay, so if it's not got a constant plugged in, then our plain x term should go away. All right, so that leaves me with the limit as h approaches 0 of 2xh plus h squared minus 4h, and we're going to divide it by h. So the limit as h approaches 0, 2x plus h minus 4. Now, who are we plugging 0 in for? The h. Okay, so that's going to give me 2x, a 0, minus 4. This is your derivative function. Okay, so we wanted a function of x. Does it make sense that I started with something quadratic and I got something that was linear? based on the investigation we did. Yes, okay? So you kind of get a little double check. You might miss some math here and there right now, but we at least know we're headed in the right direction, okay? So question about what I did with just the limit process. I want you to see all that algebra. Okay. So now that we have that general function for the derivative, we can evaluate the derivative at any point we so choose. Okay? So if I wanted to do these 3 points, f prime at 0, f prime at 1, f prime at 2, we're just going to plug them into that general function we just found. All right? So 2 times 0 minus 4 is negative 4. 2 times 1 minus 4, negative 2. And then 2 times 2 minus 4, we get 0. So we can use that general formula to evaluate as many derivatives as we so choose. Sorry, fruit tea water today. Good. All right, what questions do you have? Where do you anticipate your mistake will come? Yeah, your algebra. All right, most definitely that's where it comes. You just be careful. All right, there are some checks and balances built in, which is nice. All right, we know certain things should go away. What?
We've been going check balances and go.
Oh, sorry. Y'all gonna have to fill me in. I don't know the. Yeah. Did y'all watch the debate last night, by the way? No?
I don't think I'm gonna bring myself to do it.
I know. My mom said she would wake me up.
I watched the first.
You know, I'm too young to.
I went to bed, so I watched the first 45 minutes. Then I went to bed. It's all good. As I told my husband, if a debate is a job interview, I'm not hiring either one of them. So, anyway. God love them. All right. I wouldn't want to be on that stage, so. Would you? Go for it, sis. I'll vote for you.
I was watching it. She kept looking at him, but he didn't look at her at all.
It's true.
Oh, yeah.
Body language is interesting, isn't it? I love it. So, anyway. The communicator in me enjoys it. All right, so let's look at this one. F of x equals square root of x. Now, we've not done one using the alternate definition, and I wanted us to, okay? Because I wanted you to see why we might want to do the alternate definition. Remember that alternate definition was this one, the limit as x approaches a of f of x minus f of a over x minus a, okay? So here's one where sometimes it's nice to use the alternate definition, and I want to show you why when we get into it, okay? So again, everything's abstract. We're coming up with a function of x for the derivative, and so we're going to use this limit definition. And so if I plug everything in, so limit as x approaches a, so f of x would be square root of x minus square root of a over x minus a. And when I look at that, I'm like, well, that didn't help anything. Okay, because what value am I plugging in this limit? A, and for which variable? X, okay? So if I put a's where the x's are, what's going to happen in that limit? It's indeterminate, right? I get 0 over 0. So square root of a minus square root of a minus a. So how did we talk about fixing something that has radicals in it? We use a conjugate. So I'm going to multiply by the square root of x plus the square root of a over, not that, it's got to be a well-chosen one, square root of x plus the square root of a. All right, so we're going all the way back to those limit strategies that we talked about in the beginning, okay? Now, when we do that, that's going to leave me with the limit as x approaches a. On the top, we are just going to get two terms when we multiply because they're conjugates, right? So what's the square root of x times the square root of x? X. And what's the square root of a times the square root of a? A, and we keep the minus in the middle. On the bottom, I've got x minus a and square root of x plus square root of a. Okay, what's going to happen at this point with the algebra? Yeah, the numerator is going to cancel with that factor in the denominator. So I get the limit as x approaches a of 1 over the square root of x plus the square root of a. Okay, so now I'm ready to substitute. Okay, again, what am I plugging in? And who am I plugging it into? X. So I get 1 over the square root of a plus the square root of a, which will be 1 over 2 square roots of a. Okay? Remember, a is just another x value. And so that becomes my derivative. Okay? And we're going to call it f prime at a because a could be an x value. All right? Now, that's a lot more difficult to complete if you use the x plus h notation, all right? The radicals are nastier, the algebra is nastier, so this is sometimes, anytime I have a radical, I almost always go with the alternate definition if I'm having to do a limit, or if I start with something like 1 over x, I almost always use the alternate definition, okay? So just as a hint, that's just, you know, it just simplifies your algebra a little bit. Does it still work? Using the limit as h approaches 0? Yep, it does, okay? But the algebra is just a little bit nastier, okay? And so in your practice tonight, there are some that say use the alternate definition, and that's just for you to practice, okay? Seeing how those work. Now, why do we need this, all right? What do we need derivatives for, okay? Well, we've already talked about instantaneous rates of change, but one of the most famous problems in all of calculus is referred to as the tangent line problem, okay? Finding the equation of the line tangent to the curve at a point. Okay, that's what it means. Find the equation of the line tangent to the curve. Oh, that was aggressive. I'm looking through the window first. Hey.
Sorry, I'm gonna cut through this one.
Okay.
So aggressive.
Jababy was being aggressive.
Listen, sometimes you gotta do what you gotta do.
That's what we call him. Jababy. Okay. So anytime it talks about finding the equation of the line tangent to a curve at a point, what's nice about this tangent line, and we'll learn this later, is we use it to approximate function values that we otherwise wouldn't be able to calculate. All right? Because it would be just way too intensive. All right? So what do we need? If we're writing the equation of a line, what do you need to write the equation of a line? We need a slope. Okay? The slope equals the derivative at that point. Okay? So anytime we want to write the equation of the line tangent to a curve, we got to find the slope, which is the derivative. Okay? The derivative. Then we need the point of tangency. All right? Where are we going to be tangent? Okay, well, that's an x, and a y value. Okay, so we're going to need an ordered pair. Those are the two things that are required to write the equation of any line, a slope and a point. That doesn't change. Okay, we're just specific. We want the slope of the tangent, which is the derivative, and the point of tangency. We're going to use point slope form, that modified form that I showed you, and it's always going to look like this. Y is going to equal my slope, x minus, we'll say x1 there because it's my ordered pair, plus y1. Just remember, okay, that slope is f prime, and that y value is the function evaluated. Okay, so that's just two different ways to write it. Okay, slope times x minus x1, whatever your x value is, keep the same y. All right, if we put it in function notation, my slope is the derivative, x is my x value, my y value is x plugged into the original function. Okay, so that's where that comes from. So we're going to write equations of lines. All right, you do not have to simplify. Okay, leave it in point slope form. Don't mess with it otherwise. Okay, save yourself an arithmetic mistake. Unless it says put it in slope intercept, you do not have to. Okay, you can leave it be. Now, a normal line. Anybody know what the word normal means mathematically? Think geometry. What'd you say? No? It's a good guess, though.
Opposite of paranormal.
It is actually perpendicular. Okay, normal means a perpendicular.
I would have gone there in the end, I'm sure.
Okay, normal means a perpendicular. So basically, it is the line perpendicular to the tangent. Okay, so anytime that you're asked to find the normal line, you got to start with the tangent line first. This one's perpendicular. Okay, what's true about two perpendicular lines? They have opposite reciprocal slopes. Okay, so the slope of the normal line is the opposite reciprocal of the derivative. Okay, they have opposite reciprocal slopes. We're going to use the exact same point. All right, we're going to go through that same point of tangency. That's not going to change, but we're just going to change the slope to an opposite reciprocal. All right, and write the equation. It is a linear equation. If we can get down writing equations of tangents and normals, we've conquered most of what we need to do, okay? Because it's a huge part of what we're going to do moving forward. We'll do it so much, okay? And they're going to ask me about it in lots of different ways. So I want to do a couple of examples with you, different ways that they ask these questions regarding the tangent line. And let's see what we can do. Okay. This process will get easier as we learn the shortcuts. Today we're going to have to do the long way with the limits, okay? But the good stuff's coming. All right. The good stuff's coming. All right, so let's take a look at this one. All right, if f of 3 is equal to 7 and f prime at 3 is equal to -2, find an equation of the tangent and the normal line to the graph of f of x at the point x equals 3. Okay, so let's think about what they've given me. We know we need a slope and we need a point. We need an ordered pair. Okay, did they give me an ordered pair? Yes, what's my ordered pair? 3, 7. So I've got my point, which is 3, 7. The next thing I need is a slope. Okay. Did they give me a slope at that point? Yes. Okay. What is it? It's -2. Okay. It is my derivative at that point where x is 3. So right there in that first sentence, they gave me everything I needed. Okay. So we're going to start by writing the equation of our tangent. Okay. You must always start with y equals. Okay, always start with y equals. My slope's going to come first, so negative 2. X, what's going to go in parentheses with x? Minus 3, and then what's going to go at the end? Plus 7. Okay, so that's my tangent line. All right, the only thing I really had to know in that problem is what f prime is and how to write the equation of a line. Okay, now let's switch and do my normal line. With this equation, what's the only thing that's going to change with my normal line? My slope. Okay, it's going to be an opposite reciprocal of what I already had. What would be the opposite reciprocal of negative 2? 1/2. So my normal line is y equals 1/2. The point doesn't change, so the rest of the equation stays the same. Okay, it's almost too easy, isn't it? Compared to everything else we've been doing, right? Question. Yes, ma'am.
So you know that the slope is that because it has the prime, so it's the derivative?
Yes. Yes. Okay, and we know the slope of the normal is the opposite reciprocal of that derivative. Okay. All right, so now let's just jack it up a notch. Okay, actually it's more like, but it's okay. All right. Sorry, I like to be honest. Okay, you're welcome, trying to be honest. Okay, so let's take a look at this one. This time they didn't give it to me all nice and packaged up pretty with a bow. All right, they gave me this ugly function and they just give me a point of tangency. All right, and when they do that, that means I've got to take the derivative so that I can find the slope. All right, now you've got a couple of options here. All right, to find the slope of your tangent at 4. I'm going to actually use the alternate definition because this is a rational function. Okay, so let me show it to you. I'm going to do the limit as x approaches. My a value is 4. Okay, f of x minus f at 4 over x minus 4. And it doesn't look like I've done myself any favors to start that way, but that's how I'm going to start. All right. So let's plug in what we have and see what happens. Okay, I'm going to keep my limit. So the limit as x approaches 4, f of x is going to be 5 over x minus 1. Okay, f at 4 is going to be 5 over 4 minus 1, which is 5 over 3. And we're going to divide it by x minus 4. Okay. Now, it doesn't look like at first that I've done myself any favors, okay, because I got this nasty complex fraction, all right? This is one of the things that I noticed you guys struggle with a little bit, okay? So let's work on this complex fraction. We need to practice this. It's good for us, right? Let's start with just the two fractions in the numerator. In order to put them together, to subtract them, what has to happen? They have to have the same denominator, okay? So 1 has a denominator of x minus 1. 1 has a denominator of 3. What would be the common denominator?
3x minus
3 times x minus 1 or 3x minus 3, okay? So I know my common denominator would be the product of both of those, okay? In that first fraction, my denominator already has the x minus 1. What part's it missing? The 3, okay? So if I multiply the bottom of that fraction by 3, what do I have to multiply the top by? 3. So 5 times 3 would give me 15, okay? In the second one, I already have the 3, but I'm missing the x minus 1. So I'm going to keep the 5 that was already there and multiply it by the x minus 1. So let me just stop right there. Okay, so make sure we understand about getting a common denominator. Okay, it's just one of those weird algebra things, right, that we seem to miss sometimes. The x minus 4 is going to stay in place in the denominator. Again, this does not look very helpful. Okay, doesn't look very helpful. But what should I do next? Yeah, let's simplify that numerator of the fraction in the numerator. All right, doesn't that sound weird? So we'll take the limit as x approaches 4. That's going to give me 15 minus 5x plus 5. All right, all divided by 3 times x minus 1, all over x minus 4. Okay, so we're getting closer.
Why don't you just get rid of the x minus 1?
Because 15 does not have an x minus 1. In order to get rid of it, all right, if I divide now up here in the blue step, it takes me right back where I started. Okay, because I'd have 5 over that x minus 1 would not go away. Here, in order to be, we got to get one term on the top so that I have something in a parenthesis with x minus 1. I can't have that subtraction in there. Okay, good question. All right, so let's simplify a little bit. In that numerator of that top fraction, that's going to give me negative 5x plus 20 over 3 times x minus 1, all divided by x minus 4. Okay. Now, we're down to a single fraction divided by basically a single fraction. Okay, what do we do when we divide fractions? Same change flip, multiply by a reciprocal, all that good stuff. Do you think I need to do any factoring in that numerator up there? Bless you, bless you. Yeah, we can take it on negative 5, right? So that leaves me the limit as x approaches 4. If I pull the negative 5 out, that's going to leave me x minus 4. Oh, I'm seeing something. 3 times x minus 1. I'm going to go ahead and change to multiply. If I was dividing by x minus 4, I'm going to multiply by 1 over x minus 4. Okay. Do you see the light at the end of the tunnel? Okay. Now I've got a product here so I can reduce. Okay. So you can only reduce when you have a product. Here we had a difference, so we couldn't reduce. Right. So my x minus 4s are going to go away. And I get the limit as x approaches 4 of negative 5 over 3 times x minus 1. Now we can substitute. Okay, finally, right? We had to do a lot of algebra, but now we can substitute. And if we do that, that gives me negative 5 over 3 times 4 minus 1, or negative 5 over 9. This is my derivative at 4. Okay. Now, have we answered the question? No, but we're closer. Okay, we have not answered the question, but we are closer than where we started. We have a slope. Okay, we have a slope, which we know was one piece that we needed. What was the other piece we needed? The ordered pair. Okay. So basically, I know my x value is 4, so I need f at 4, all right? That's going to go back in the original function, okay? Back in the original function. So 5 over 4 minus 1, which is 5/3. And so there's my ordered pair, 4, 5/3, all right? One step closer. Have we answered the question? Nope, because what is it asking me for? Equation of the line, okay? So I had to do all that work to get the pieces. Now we're going to answer the question, okay? The equation of the tangent line, y equals, my slope is going to come first, x minus my x value plus my y value. Aren't you glad that we don't have to simplify? To walk your face. Okay. That's a lot. Okay, that's as hard as those problems get. Okay, which is the good news. I like to show you a tough one so you got something to go back and look at. Okay, hopefully you get a nicer function, something quadratic, right? Something linear, that we could just do the normal definition, all right, for a derivative. We wouldn't have to use the alternate. Okay, but I like to show you something tougher. All right, to process that for a second. Questioning your life choices. Since day one, right, Oki? It's okay. Sometimes I question mine. I had no idea that was going to happen, by the way. So, when they called y'all out for AP Scholars.
All nerds. And they know we're awkward people. I don't know why he did that to us. You have to know it's demographic.
I don't know what, I think it was cute.
I thought it was good.
It was cute. You need to know it's demographic here. Like, us.
No, I think I liked it.
It was sweet, but
Like Sam said he liked
They
it.
literally have never done that to anyone else before. We're scarred for life, and it's all his fault. Like,
I'm one bully toast.
Y'all are not scarred for life.
No. I
Okay.
think you'll look
I
back
actually
and
don't
be like,
think
oh,
I
that was
did.
okay, maybe I'm being a little dramatic, but still. It's not for me, it's for everyone else that has done it as well.
All right, look at this one. Okay. One like this is similar to what you're going to see on the exam. Okay. By the time we get to the one above on the exam in a multiple choice, you're going to know the shortcuts and it's going to go a lot quicker. Okay. But let's look at this one. This one was actually a multiple choice I pulled from some practice material they gave me, but I just took the multiple choice out. Okay. You're welcome. All right.
Thanks a lot.
So let's take a look. So here they give me a function. Okay. And then they give me a tangent line. So they gave me the tangent line right there. Okay. It says, shown above is the graph of the differentiable function f along with the line tangent to the graph of f at x equals 2. Okay. What is the value of f prime at 2? So let's think about what are they asking me. Okay. Because all I have is a graph, I need to know what is the slope of the tangent line. Okay. That's all I need. All right. So it's asking me at what is this? What is the slope of the tangent line? And so you're going to see pieces of this kind of problem show up in lots of multi-step things that happen, okay? Moving forward. So let's look. Let's see if we can find a good value and count the slope. What does the slope seem to be? 1/2? I would agree. F prime at 2 is 1/2. We're just counting the slope of that tangent line from one point to the other. That's legitimately all it's asking you for. That's it. Yeah. Okay. It is 1/2. Now let's think about what answers do you think they might put in the multiple choice, because I think it's important. Know that when they do your answers, when they cut them back to 4, there used to always be one that was obviously wrong. Okay, so when we had 5, there was one that was obviously wrong. Okay, well that's no longer there. And we know the right answer's there. So what do you think they do to get the other 3?
Probably have to
What do you mean?
run over right.
Yep, so they might do one where it's transposed, right? So they're doing common mistakes, so I think 2 would be an option. All right, what else do you think might be an option? 3. Okay, why do you think 3 would be an option? Because that's where they intersect, okay? So it's those kind of things. So that's why it's going to be really important that you're looking at the graph and looking at the question, because they're going to put things, they're going to be those quick common mistakes that you're going to make as an answer choice. Okay, so it's not like the ACT when you're like, I got 75 and 74.2 was on here. I'm taking 74.2, right? I don't know if that's what y'all do, but that's what I did. Okay, so just know that they're going to, when they write a question, they make the common mistakes and then they put the answer on there. Okay, so just know that. You're going to get good at figuring that out, all right, the more we do. All right, so here's what I'd like to do. All right, let me give you some practice. Okay, this is out of your text. It's on page 111. Right, 1, 3, 5, 7, 9. You need to practice doing some of these limits. Okay, 10, 11, 18, and 19. Writing some equations of tangent lines. I personally will just feel better if we don't have the quiz tomorrow. Okay, that's just me. I don't want to put y'all in a bad spot. Okay, but I don't know that I want to do it on Monday either. So I don't know. Let me think on that. Okay, it's not tomorrow. Okay, because I do need to talk to you about 2.3. 2.3 is super easy going forward. So more than likely that's what we'll do tomorrow, and then I'll go ahead and do 2.4 on, I don't know. I'll just think about it and let you know. I don't anticipate giving you a quiz on Friday, so let me just put it that way. Okay, so your quiz might move to Tuesday of next week or Monday, but we'll talk about that. Okay, do y'all have a preference? Okay, but I need you to practice some of these limits tonight so that we can check a few tomorrow. Okay, just to make sure you're feeling good about that. Because that is a big chunk of what's on this quiz. All right, it's showing me the limit and doing the work, writing the equation of the tangent line. Okay, so do that for me. Go ahead and click in and do the wrap up. It should be on, I don't know if I changed the dates or not, but it's on the post for 2.2, which I think was yesterday's. Okay, and do your wrap up. And I'll go in and clean up Google Classroom with the dates and stuff this afternoon a little bit. Okay. You can take a derivative. Are you on the post for today or for yesterday? Okay, go to the one from yesterday. It's the one from yesterday. Is it right? Yes. It says different. It does. It just means you should take a derivative. And you can throw your sticky note away unless you want to be your number the rest of the day.